Imagine a star so enormous that if you placed it where our sun is right now, its surface wouldn't just swallow Mercury. It wouldn't just swallow Venus or Earth or Mars. It wouldn't even stop at Jupiter or Saturn. This star would stretch so far outward that its glowing edge would reach past the orbit of Saturn, engulfing nearly everything we think of as the solar system. Light itself, traveling at 300,000 kilometers per second, would need over 8 hours just to circle this star once. And here's the part that will keep you up tonight. We're not even completely sure this is the largest star out there. The true answer is stranger, more uncertain, and more extreme than almost anyone realizes. This is a story about the biggest things that have ever existed. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know. The sun. You see it every day. It rises in the east, moves across the sky, and sets in the west. It's been doing that for as long as humans have existed. It feels permanent, reliable, impossibly large. And from our perspective down here on Earth's surface, it genuinely is large. The sun has a diameter of about 1,400,000 kilometers. If you could somehow line up Earth side by side across the face of the sun, you would need roughly 109 of them to stretch from one edge to the other. And that's just a line across its middle. If you think about volume, about filling the sun's interior with Earth the way you might fill a jar with marbles, you could fit approximately 1,300,000 Earths inside. Every mountain, every ocean, every continent, every city, every person who has ever lived, all of it exists on a planet that could be dropped into the sun over 1,000,000 times and still not fill it up. To get an intuitive feel for how large the sun really is, think about it this way. If you could fly a commercial jet straight across the diameter of the sun at roughly 900 kilometers per hour, the flight would take about 65 days. More than 2 months of non-stop flying, just to get from one side of the sun to the other. Even light, the fastest thing in the universe, needs about 4.5 seconds to cross the sun's diameter. That's 4.5 seconds at 300,000 kilometers per second. The sun is so wide that light itself requires a measurable amount of time to traverse it. The sun dominates our solar system in a way that's difficult to overstate. It contains 99.86% of all the mass in the entire solar system. Everything else, all 8 planets, all their moons, all the asteroids and comets combined, makes up only 0.14%. Jupiter, the largest planet in our solar system, is itself so enormous that over 1,300 Earths could fit inside it. And yet Jupiter is still roughly 1,000 times smaller than the sun by volume. The sun isn't just the biggest thing in our neighborhood. It is the neighborhood. Everything else orbits it because its gravity is so overwhelmingly dominant that nothing nearby can resist its pull. The surface of the sun reaches about 5,500 degrees Celsius, hot enough to vaporize every known material. The core, where nuclear fusion occurs, reaches approximately 15 million degrees Celsius. Under these extreme conditions, the sun converts roughly 600 million tons of hydrogen into helium every single second. That process releases energy so immense that the sun produces more energy in 1 second than all of human civilization has generated in its entire history. The sun is powerful, bright, massive, and by every human standard, Enormous. So here's the question that should change your perspective tonight. What if the sun isn't actually big? What if I told you the sun is a fairly small star? Not the smallest, but nowhere near the largest. What if the sun, this object that dominates everything we know, that could swallow over 1 million Earths, is actually average at best? Because that's the truth. Astronomers classify the sun as a G-type main sequence star, sometimes called a yellow dwarf. That word, dwarf, should tell you something. Compared to the true giants of the stellar world, the sun is unremarkable. It sits in the middle of the pack in terms of size, temperature, and brightness. It's a perfectly ordinary star in a galaxy that contains somewhere between 100 billion and 400 billion stars, most of which differ wildly from each other in size, brightness, temperature, and age. And some of those stars are so preposterously large that the sun would vanish like a speck of dust beside them. But before we start climbing that ladder of size, before we meet the true monsters, there's something important we need to clarify. Because when people say the largest star, that phrase can mean very different things depending on what you're actually measuring. And understanding this distinction is essential to everything that comes next. When astronomers talk about the largest star, they almost always mean the star with the biggest radius. The star that stretches farthest from its center to its outer edge. This is the measurement that captures what most of us intuitively mean by size. How much physical space does this thing take up? How far does it extend in every direction? If you could somehow hover nearby and look at it, how enormous would it appear? That's radius. And radius is what determines whether a star could engulf planets, swallow entire orbits, or stretch across distances that normally separate whole worlds from one another. But here's where things get counterintuitive. Radius is not the same as mass. You might assume that the biggest stars must also be the heaviest. That a star 1,000 times wider than the sun must also be 1,000 times heavier. But that's not how it works at all. Some of the largest stars by radius are surprisingly light for their physical size. They're enormous, absolutely, but much of that volume is made up of gas so thin and diffuse that it barely qualifies as matter. The outermost layers of the very largest stars can be less dense than the best laboratory vacuum we could produce on Earth. Think about that for a moment. You could technically be inside one of these stars, and the gas around you would be thinner than what scientists consider a vacuum. These stars are like cosmic soap bubbles, unimaginably wide, but not nearly as heavy as their size would suggest. A star with a radius 1,000 times the sun's might have only 10 to 40 times the sun's mass, because almost all of that volume is gossamer-thin gas gently drifting at the edge of space. Meanwhile, some of the most massive objects in the universe are extraordinarily compact. Neutron stars, the collapsed remnants of stars that have already exploded, can contain more mass than our sun, packed into a sphere only about 20 kilometers across. That's roughly the size of a city, holding the mass of an entire star. Black holes are even more extreme. The mass is compressed into a region so small and so dense that nothing, not even light, can escape it. Mass and size simply don't correlate the way our everyday intuition would suggest. There's also luminosity, which measures how much total energy a star radiates into space. A star can be extraordinarily luminous without being physically wide. Blue supergiant stars, for example, can outshine the sun by hundreds of thousands of times, while being far smaller in radius than the biggest red supergiants. Luminosity depends on both temperature and surface area together. A small, extremely hot star can pour out more energy than a large, cool one. So luminosity and radius are separate measurements that don't necessarily track together either. The takeaway is this: when we talk about the largest star, we mean the star with the greatest radius, the one that occupies the most physical space. Not the heaviest, not the brightest, but the widest. And as we're about to discover, the stars that claim this title are so absurdly large that our entire solar system starts to feel like a marble in a cathedral. Now, to understand why some stars become so enormous while others remain small, you need to understand something about how stars live and die. A star's size isn't fixed for its entire existence. Stars change, they evolve, they age, and as they age, some of them swell to truly extraordinary dimensions. Every star begins its life the same basic way: a cloud of hydrogen gas and dust floating in interstellar space begins to collapse under its own gravity. As the material falls inward, it heats up, pressure builds. Eventually the core becomes so hot and so dense that hydrogen atoms begin fusing into helium. This nuclear fusion releases tremendous energy, and that energy pushes outward against the inward crush of gravity. The star reaches a balance, gravity pulling inward, fusion pushing outward. As long as this balance holds, the star remains stable. A star in this stable, balanced state is called a main sequence star, and this is the longest phase of any star's life. Our Sun has been in this phase for about 4.5 billion years, and it will remain here for roughly another 5 billion. During this time, its size stays relatively constant. It's in equilibrium. But this balance does not last forever. Eventually, a star begins to run out of hydrogen fuel in its core. When that happens, the core starts to contract because there's no longer enough outward pressure to hold it up against gravity. As the core contracts, it heats up dramatically. The layers of hydrogen just outside the core, which weren't previously hot enough to sustain fusion, now find themselves in an environment hot enough to ignite. Hydrogen fusion begins in a shell surrounding the now inert helium core. This is where things get dramatic. The energy pouring outward from this hydrogen-burning shell is enormous, and the star's outer layers respond by expanding. The star swells. It grows larger and larger, its outer atmosphere billowing outward like a balloon being inflated in slow motion. As it expands, the surface cools, because the same amount of energy is now spread over a vastly greater surface area. The surface temperature drops, and the star shifts in color from white or yellow to orange, and eventually to red. The star has become a red giant. This is what will happen to our own Sun in about 5 billion years. It will exhaust the hydrogen in its core, begin shell burning, and balloon into a red giant roughly 100 to 200 times its current diameter. That sounds dramatic, and it is dramatic by human standards. The Sun as a red giant will engulf the orbits of Mercury and Venus, and likely scorch or consume the Earth. But in the world of stellar giants, 100 or 200 solar radii is actually modest. It's barely the foothills of the mountain we're climbing. For stars that begin their lives significantly more massive than the Sun, the story becomes far more extreme. A star born with 10 or 20 times the mass of the Sun doesn't just live a proportionally shorter life. It lives a drastically shorter life, because more massive stars burn through their fuel at exponentially higher rates. The Sun will shine for roughly 10 billion years total. A star with 20 times the Sun's mass might last only 8 to 10 million years before exhausting its fuel. That's roughly 1,000th the Sun's lifetime. These massive stars live fast and die young by cosmic standards. When these heavy stars begin running out of fuel, they don't just become ordinary red giants, they become supergiants, and in the most extreme cases, they swell into hypergiants, stars so enormous and so distended that their outer layers are barely held together by gravity. Stars that push against the very limits of what can structurally exist. Stars whose surfaces are so far from their cores that the connection between the two becomes almost tenuous. The outermost layers drift in a kind of no man's land, too loosely bound to call themselves truly part of the star, yet too gravitationally attached to float away entirely. Let's start climbing the ladder of stellar size, because watching these numbers grow is one of the most powerful ways to feel the true scale of what's out there. We'll begin with a few stars you might recognize. Arcturus is one of the brightest stars in the night sky. If you follow the arc of the Big Dipper's handle, it leads you right to it. Arcturus is a red giant star located about 36 light years from Earth. It has a radius roughly 25 times larger than the Sun. If you placed Arcturus where the Sun is, its surface would extend well past the orbit of Mercury. Mercury, which orbits about 58 million kilometers from the Sun, would be completely engulfed. The innermost planet in our solar system would simply vanish, swallowed whole by a star whose burning atmosphere stretches far beyond Mercury's path. If you flew a commercial jet across the diameter of Arcturus at 900 kilometers per hour, the trip would take roughly 4.5 years of non-stop flight. That's 4.5 years just across one star. And yet Arcturus is considered a perfectly ordinary red giant. There is nothing exotic or extreme about it. It's simply a star that has aged beyond its main sequence phase and expanded. 25 times the Sun's radius sounds impressive until you realize where this ladder leads. Aldebaran is the bright orange star that marks the eye of the constellation Taurus. It sits about 65 light years from Earth and has a radius roughly 44 times larger than the Sun. Placed at the center of our solar system, Aldebaran's surface would stretch past the orbit of Mercury and reach a significant fraction of the way toward Venus. Light would need roughly 3.5 minutes just to cross it from one side to the other. Aldebaran is nearly twice the size of Arcturus, and yet it too is simply a regular red giant. Stars this size are common throughout the galaxy. Hundreds of millions of them exist in the Milky Way. Our own sun will eventually swell to a comparable size, billions of years from now. Now let's take a significant jump. Rigel is the brilliant blue-white star that marks the left foot of the constellation Orion. Unlike Arcturus and Aldebaran, Rigel is not a red giant. It's a blue supergiant, an extremely hot, extremely luminous star, located roughly 860 light years from Earth. Rigel has a radius about 79 times larger than the Sun. Its surface would extend past Mercury's orbit and approach the orbit of Venus. But what makes Rigel truly remarkable isn't size alone. It's the combination of size and temperature. Rigel's surface burns at about 12,000 degrees Celsius, more than twice as hot as the Sun. Because it's both large and scorching, Rigel is extraordinarily luminous. It shines with the power of roughly 120,000 suns. If you replaced our sun with Rigel, the Earth wouldn't just be uninhabitable. It would be blasted by radiation so intense that the very rocks on the surface would glow. A jet crossing Rigel's diameter would need about 14 years of continuous flight. And yet, Rigel is still not among the truly largest stars. It's impressive, but it's a stepping stone to something far more extreme. Because when we move from blue supergiants to the red supergiants, the numbers jump into territory that starts breaking our sense of scale. Antares is the brilliant reddish star at the heart of the constellation Scorpius, one of the most prominent summer constellations. It's a red supergiant located about 550 light-years from Earth. Antares has a radius estimated at roughly 680 times the radius of the Sun. Not 25 like Arcturus, not 44 like Aldebaran, not 79 like Rigel, 680. If you placed Antares at the center of our solar system, its surface would extend past the orbit of Mars. Mercury, Venus, Earth, and Mars would all be inside this star. They wouldn't orbit it. They would be consumed by it, existing within its atmosphere, dissolved into its incandescent gas, gone. The asteroid belt beyond Mars would sit just outside the star's visible edge, bathed in searing radiation. Light needs roughly 53 minutes, just under an hour, to cross Antares from one side to the other. A commercial jet making the same crossing would require approximately 120,000 years. Think about that. An airplane flying non-stop for over 100,000 years just to cross one star. And then there's Betelgeuse, arguably the most famous star in the sky after the Sun. Betelgeuse marks the shoulder of the constellation Orion and is easily recognizable by its reddish-orange hue. It's a red supergiant located somewhere between 500 and 700 light-years from Earth, depending on which measurement you use, and its radius is estimated at roughly 700 to possibly over 1,000 times the radius of the Sun, depending on the study, the technique, and when the measurement was taken. Placed at the center of our solar system, Betelgeuse would engulf everything out to at least the orbit of Mars, and possibly stretch toward the orbit of Jupiter. What makes Betelgeuse especially fascinating is that it's unstable. It physically pulsates, swelling and contracting over irregular timescales. Its brightness visibly fluctuates over months and years. In late 2019 and early 2020, Betelgeuse underwent a dramatic dimming event, losing a significant fraction of its usual brightness over the course of weeks. For a brief moment, astronomers and the public wondered whether the star was preparing to explode as a supernova. It wasn't. The dimming was most likely caused by a massive plume of hot gas expelled from the star's surface, which cooled and formed a cloud of dust that temporarily blocked our view. But the event served as a reminder that Betelgeuse is a star nearing the end of its life. It has burned through almost all of its available fuel. Within the next 100,000 years or so, which is a blink of an eye in cosmic terms, Betelgeuse will exhaust its remaining energy reserves and collapse. The result will be a core collapse supernova, one of the most violent and energetic events in all of nature. When it happens, Betelgeuse will briefly shine as brightly as the full moon in Earth's night sky, visible even during the day. But here is what should genuinely astonish you. Antares and Betelgeuse, these colossal red supergiants with radii 600 to over 1,000 times the Sun, stars that could swallow the inner solar system whole, stars so large that light itself needs hours to cross them. These are not the largest stars we found. They're not even close. In the hierarchy of stellar size, they're impressive, absolutely. But above them, far above them, are stars so enormous that even Betelgeuse begins to look modest by comparison. Stars whose dimensions push into a realm where our entire solar system stops being a useful frame of reference because the star simply doesn't fit inside it anymore. Stars that would extend past Jupiter, past Saturn, into the cold outer reaches of space where we normally think of ice giants and frozen comets. Those stars exist. We've measured them. We've catalogued them. And the scale of what they represent is going to require us to abandon nearly every sense of proportion you've built up so far tonight. Because everything we've discussed, the sun, the red giants, the supergiants, all of it is just the warm-up. We've seen red giants like Arcturus and Aldebaran, stars dozens of times the sun's radius. We've seen red supergiants like Antares and Betelgeuse, stars hundreds of times wider than the sun, objects large enough to swallow the inner solar system whole. But now we need to cross a line. We need to leave behind the merely enormous and enter the realm of the genuinely extreme. Because above the supergiants, above even the largest stars most people have heard of, there exists a class of stellar objects so swollen, so distended, so physically vast that they challenge the boundaries of what a star can even be. These are the hypergiants and the extreme red supergiants. And the scale of what they represent is going to require you to abandon almost every intuitive comparison you've relied on so far. To understand why these stars are so extraordinarily large, you first need to understand what's happening inside them. Because their size isn't random. It's the direct result of a physical process that spirals toward ever greater extremes as a massive star approaches the end of its life. Remember what we discussed earlier about how stars work? A star is fundamentally a balance between two opposing forces. Gravity pulls everything inward, trying to crush the star into the smallest possible space. Nuclear fusion in the core pushes outward, generating energy and pressure that resists that collapse. For most of a star's life, these two forces are in equilibrium. The star is stable, it holds a relatively consistent size. But when a massive star, one born with perhaps 15 or 20 or 30 times the mass of the sun, starts to exhaust the hydrogen in its core, this equilibrium begins to break down in dramatic fashion. The core, no longer generating enough energy from hydrogen fusion, contracts under its own gravity. As it contracts, it heats up enormously. Eventually it becomes hot enough to begin fusing helium into carbon. This buys the star some time, but not much. Helium fusion runs out much faster than hydrogen fusion did. The core contracts again, heats up again, and begins fusing carbon into heavier elements like neon and oxygen. Each successive stage of fusion is shorter than the last. Hydrogen fusion might last millions of years. Helium fusion lasts hundreds of thousands of years. Carbon fusion might last only a few thousand years. By the time the core reaches silicon fusion, the final stage before collapse, it might last only a matter of days. During all of this, something remarkable is happening in the layers above the core. Each time a new fusion stage ignites in the core, the energy output changes. The layers of material surrounding the core respond by expanding outward. The star swells. Multiple shells of fusion can burn simultaneously, each one adding energy, each one pushing the envelope further and further outward. The outer atmosphere of the star balloons to extraordinary proportions. And because this atmosphere is expanding into the vacuum of space, it becomes increasingly tenuous. The gas at the star's surface, if you can even call it a surface, thins out to an almost unimaginable degree. This is a critical point. The outermost layers of the very largest stars are not solid. They're not even dense gas. They are wisps of material so thin that they approach the conditions of a laboratory vacuum. On Earth, we think of a vacuum as empty space, but the outer edge of a red hypergiant contains gas that is in some cases less dense than the best vacuum chambers we've ever built. The star technically extends that far. That diffuse material is still gravitationally bound to the star, still part of its structure, still radiating light. But it's so thin that if you could somehow stand in it, you wouldn't know you were inside a star. There would be no sensation of being surrounded by stellar material. You would see a faint reddish glow in every direction, and instruments would tell you that yes, there are atoms here, but your human senses would register nothing but emptiness. This is why these stars can be so physically enormous without being proportionally massive. Their cores might contain only 10 to 40 solar masses of material, but that material's energy output drives an outer envelope so vast it can stretch across billions of kilometers of space. The star is essentially a dense hot engine surrounded by an incomprehensibly large atmosphere of almost nothing. But there is a limit. Stars cannot grow without bound. There is a ceiling, a physical wall that prevents a star from simply inflating forever. This limit is called the Eddington luminosity, named after the British astrophysicist Arthur Eddington, who first described it in the early 20th century. The Eddington limit is the maximum luminosity a star can sustain before the outward pressure of its own radiation overwhelms the inward pull of its gravity. Think of it this way: light carries momentum. When photons stream outward from a star's interior, they push on the material in their path. For most stars, this radiation pressure is far weaker than gravity, and the star holds together easily. But for the most massive and luminous stars, the radiation pressure becomes ferocious. The photons pouring outward from the core are so numerous and so energetic that they begin to physically shove the outer layers of the star away from the center. If a star's luminosity exceeds the Eddington limit, the radiation pressure wins. The outer layers are no longer gravitationally bound. They are blown off into space. The star doesn't just lose mass slowly through stellar winds. It hemorrhages material in violent eruptions, shedding enormous quantities of gas in relatively short periods of time. The most extreme hypergiants exist right at this boundary, balanced on a knife's edge between holding together and flying apart. Their luminosities hover near or occasionally exceed the Eddington limit, which is why their mass loss rates are so extraordinary. They are not gently aging. They are being torn apart from the inside by their own light. Every photon generated in the core is another tiny push against the tenuous outer layers. Collectively, those pushes add up to a force that rivals gravity itself. The star survives, but barely. Its outermost layers are only loosely attached, drifting at the boundary between belonging to the star and escaping into space. Any disturbance, a convective plume larger than usual, an instability in the fusion shells, a slight change in the core's energy output can tip the balance and send enormous quantities of material streaming outward. This is why these stars are surrounded by such complex nebulae of ejected gas. They're not just dying, they're disintegrating in slow motion, unraveling from the outside in as their own luminosity tears them apart. This also explains why there is an upper bound to how large a star can get. A star that tries to be bigger than the physics allows would simply eject its excess material. Its outer layers would be blown away faster than they could be maintained. There is a maximum radius, a maximum luminosity, and a maximum mass that a star can sustain before it crosses the line from bloated but intact to actively falling apart. The stars we're about to meet are dancing on that line. They are the largest things that stellar physics permits. Go any further, and the star ceases to exist as a coherent object. There's another process making things worse, or more spectacular, depending on your perspective. Convection. In these giant stars, enormous cells of hot gas rise from deep within the star, reach the surface, cool, and sink back down. On the Sun, these convection cells are relatively small, maybe 1,000 kilometers across. In a red supergiant, a single convection cell can be larger than the orbit of Earth around the Sun. These titanic plumes of rising gas disturb the star's surface, creating enormous bubbles and irregularities. They contribute to the star's instability, causing it to pulsate irregularly, swelling and contracting on timescales of months or years. The star's radius isn't fixed. It fluctuates. The edge of the star heaves in and out like a slow, cosmic breath. On top of all this, these extreme stars are losing mass at a staggering rate. The outermost layers are so loosely held by gravity that stellar winds, driven by radiation pressure from the luminous interior, continuously blow material off the star and into surrounding space. A star like the Sun loses mass through its solar wind, but the amount is negligible, perhaps 1/10 trillionth of its mass per year. The most extreme supergiants and hypergiants can lose the equivalent of an entire Earth's mass every few years. Some lose a solar mass every 10,000 to 100,000 years. Over their lifetimes, they shed enormous quantities of material, creating vast nebulae of gas and dust surrounding themselves. These stars are literally evaporating, falling apart, shedding their outer layers into the void, even as their cores race toward collapse. This is the physical reality behind the largest stars in the universe. They are not stable, solid, well-defined objects. They are bloated, pulsating, violently unstable structures that are simultaneously expanding under internal pressure and disintegrating under mass loss. They exist at the ragged edge of what stellar physics allows. Push them any further and they would simply cease to be stars at all, dissolving into expanding clouds of gas. Now, let's meet some of these monsters. VY, Canis Majoris, is one of the most famous extreme stars in astronomy. It sits roughly 3,900 light-years from Earth in the constellation Canis Major, the same constellation that contains Sirius, the brightest star in the night sky. But while Sirius is a relatively modest main sequence star, only about twice the Sun's mass, VY Canis Majoris is something else entirely. It is a red hypergiant, one of the most luminous and physically largest stars ever discovered. The radius of VY Canis Majoris has been estimated at roughly 1,400 to 1,500 times the radius of the Sun. Let that number settle in your mind for a moment. 1,400 to 1,500 solar radii. This means VY Canis Majoris is so wide that if you placed it at the center of our solar system, its surface would extend beyond the orbit of Mars, beyond the asteroid belt, beyond the orbit of Jupiter, and approach or reach the orbit of Saturn. Mercury, Venus, Earth, Mars, and Jupiter, 5 planets, including the largest planet in our solar system, would all be inside this single star. They would not orbit it. They would simply cease to exist, vaporized and absorbed into the star's atmosphere long before you ever reached its visible edge. Light, traveling at 300,000 kilometers per second, would need approximately 6 hours to travel around the circumference of VY Canis Majoris. 6 hours for light. If you tried to fly around this star in a commercial jet at 900 kilometers per hour, that flight would take approximately 850 years. You could have started your journey during the late Middle Ages, flown non-stop for nearly a millennium, passing through the Renaissance, the Age of Exploration, the Industrial Revolution, both World Wars, the Space Age, and the Digital Age, and you still wouldn't be back where you started. One lap around one star .v Canis Majoris is also extraordinarily luminous. It shines with roughly 270,000 to 300,000 times the luminosity of the Sun. If you replace the Sun with VY Canis Majoris, the amount of energy hitting Earth would be so overwhelming that the planet would be vaporized almost instantly. But of course, Earth wouldn't even be outside the star. It would be deep within its interior, roughly 1/3 of the way from the core to the surface. Imagine you could somehow travel inward through VY Canis Majoris, starting at the very outermost edge, where the star's atmosphere dissolves into interstellar space. You begin your journey at what corresponds to the orbit of Saturn in our solar system. At first, you notice almost nothing. The gas around you is thinner than any vacuum on Earth. Space seems essentially empty. Your instruments register trace amounts of hydrogen and helium, but your sensors perceive nothing. As you travel inward, the gas slowly thickens. A very faint reddish glow begins to appear in every direction around you, so dim at first that you might mistake it for your imagination. You pass through what would be the orbit of Jupiter. The glow deepens. You can now see it clearly. A warm, dull red luminescence, filling the space around you as far as you can see in every direction. There are no sharp boundaries, no walls, no structures, just an infinite seeming haze of gently glowing gas that gets imperceptibly denser as you go deeper. You cross what would be the orbit of Mars. The glow is now strong enough to read by, a deep crimson light that casts everything in shades of red. The gas is still thin by Earth standards. You could wave your hand and feel nothing, but it is unmistakably there. Temperature readings climb. You are now well inside a star, surrounded on all sides by a stellar material, and yet the experience is less like being inside a furnace and more like drifting through an endless, dimly lit fog. The violence, the heat, the crushing density, all of that is still ahead of you. Thousands of solar radii deeper at the star's tiny, furiously burning core. Most of VY Canis Majoris is atmosphere, a titanic, almost empty atmosphere stretching across billions of kilometers. What makes VY Canis Majoris especially dramatic is the enormous nebula of material surrounding it. This star is shedding mass at a furious rate. Observations have revealed a complex, asymmetric cloud of ejected gas and dust, extending far beyond the star itself. Arcs, knots, and filaments of expelled material surround VY Canis Majoris like the remnants of slow-motion explosions. These structures were produced by episodic mass loss events, moments when the star ejected particularly large amounts of material in specific directions. Some of these ejection events release material equivalent to several times the mass of Jupiter in a single outburst. The total amount of mass VY Canis Majoris has shed over its lifetime is enormous. It may have started its life with as much as 40 to 50 solar masses, and has since lost a significant fraction of that original mass to space. VY Canis Majoris will not live much longer by cosmic standards. Within the next 100,000 years, possibly much sooner, it will exhaust the last of its nuclear fuel. When that happens, the core will collapse and the star will explode as a supernova, or possibly a hypernova, an even more energetic explosion that may be associated with a gamma ray burst. The explosion will scatter the star's remaining material across interstellar space, enriching nearby gas clouds with heavy elements that will eventually form new stars and planets. But for years, VY Canis Majoris was not considered the largest known star. That title belonged to a different object, one that captured the public imagination and appeared in countless comparison videos and infographics. That star is UY Scuti. UY Scuti is a red supergiant, possibly a red hypergiant, located approximately 5,200 light-years from Earth in the direction of the constellation Scutum, near the rich star fields of the inner Milky Way. It was first catalogued in the 1860s, but its truly extraordinary nature wasn't recognized until 2012, when a team of astronomers published measurements suggesting its radius was roughly 1,700 times the radius of the Sun. 1,700 solar radii. That figure, if accurate, would make UY Scuti significantly larger than VY Canis Majoris, significantly larger than Betelgeuse, significantly larger than anything else known at the time. It became, almost overnight, the most cited answer to the question, what is the biggest star in the universe? The numbers that accompanied UY Scuti's measurements were staggering. At 1,700 solar radii, UY Scuti, placed at the center of our solar system, would extend well past the orbit of Jupiter and reach approximately the orbit of Saturn. Saturn orbits at roughly 1.4 billion kilometers from the Sun. The surface of UY Scuti, that tenuous, diffuse, barely there outermost layer of cooling gas, would sit at about that distance. Nearly everything we consider our solar system would be inside this one star. The 4 rocky planets gone. Jupiter gone. Only Saturn would be near the star's edge, and even that would depend on the exact measurement used. The volume implied by UY Scuti's estimated size is almost impossible to grasp. If the radius is truly 1,700 times the Sun's, then the volume is roughly 5 billion times the volume of the Sun. 5 billion suns could fit inside at UY Scuti. And remember, the Sun itself can hold over 1.3 million Earths. So the number of Earths that could fit inside UY Scuti is approximately 6.5 trillion. 6.5 trillion Earths. Every human, every city, every ocean, every mountain on our planet could be replicated 6.5 trillion times, and all of those copies would fit inside one star. Every person who has ever lived, replicated 6.5 trillion times over, would still occupy a volume smaller than UY Scuti. If light takes about 4.5 seconds to cross the diameter of our Sun, then crossing the diameter of UY Scuti would take light roughly 2 hours and 7 minutes. A beam of light, the fastest thing in the universe, needs over 2 hours to travel from one side of the star to the other. A commercial airplane making that same crossing would require over 300,000 years. You could have started your flight when the first anatomically modern humans were just appearing on the savannas of Africa, flown continuously for the entire duration of our species' existence, and you would not yet be halfway across. Y Scuti's luminosity is estimated at roughly 340,000 times the luminosity of the Sun. It pours energy into space at a rate that dwarfs our star by hundreds of thousands of times over. And yet, if you look up at the night sky, you will never see UY Scuti with your naked eyes. It's too far away and too obscured by interstellar dust and gas between us and it. This colossal object, one of the largest things we've ever found, is completely invisible to the unaided human eye. You need a telescope to even know it exists. Now, imagine what it would be like to see UY Scuti up close. Picture a hypothetical planet orbiting this star at a safe distance, say at the distance where Neptune orbits our Sun, roughly 4.5 billion kilometers out. From the surface of that planet, looking back toward UY Scuti, you would see the sky dominated by an immense red orb. Not a disk the way we see the Sun from Earth, appearing about half a degree across. UY Scuti from this distance would stretch across a significant portion of the visible sky, dozens of times wider than the full moon appears from Earth. It would be like looking at a wall of dull crimson light covering a vast arc of your horizon. The light itself would be dim compared to what we experience from our Sun, because UY Scuti's surface is cool, only around 3,000 to 3,500 degrees Celsius. The landscape around you would be bathed in a perpetual reddish twilight. Shadows would have soft, diffuse edges because the light source is so enormous that it illuminates from many angles at once. There will be no harsh, directional sunlight, just an all-encompassing red glow, coming from an object so wide that your brain would struggle to register it as a single thing. And if you watched over weeks and months, you would see the surface change. Great dark patches would appear and vanish as enormous convection cells, each wider than Earth's orbit around the Sun, churned slowly across the face of the star. The star would seem to breathe, its edge gently swelling and receding as pulsations rippled through its distended atmosphere. But UY Scuti and VY Canis Majoris are not the only contenders in this extreme category. There are other stars that rival or potentially exceed them, and each one adds to the picture of just how enormous stellar objects can become. Whoa. G64 is a red supergiant located not in the Milky Way, but in the Large Magellanic Cloud, a satellite galaxy of our own that sits roughly 160,000 light-years away. This makes WOA G64 particularly challenging to study. At that immense distance, even a star this large appears as little more than a point of light in our telescopes. But careful observations have yielded an estimated radius of roughly 1,400 to 1,600 solar radii, placing it in the same league as VY Canis Majoris, and potentially approaching UY Scuti. What makes WOA G64 especially interesting is that it's surrounded by a thick torus of dust, a ring-shaped cloud of material that the star has expelled over time. This dust shroud makes the star appear dimmer than it actually is, complicating efforts to determine its true luminosity and therefore its true size. The star is essentially hiding behind its own debris, wrapping itself in the material it has shed. ML Cygni is another extreme red supergiant, located roughly 5,300 light-years from Earth in the constellation Cygnus. Its estimated radius varies between studies, but most estimates place it at roughly 1,300 to 1,700 solar radii. Like UY Scuti, NML Cygni sits in a region of the sky dense with interstellar dust, making precise measurements difficult. The star is also one of the most luminous cool stars known, radiating roughly 270,000 times the luminosity of the Sun. It is actively losing mass at an enormous rate, surrounded by a complex envelope of expelled gas and dust. Massive emissions, naturally occurring microwave amplifications in the surrounding gas, have allowed astronomers to study the material flowing away from NML Cygni in detail. These observations reveal a star in the process of violently shedding its outer layers, throwing material into space in episodic bursts that create shells and arcs of gas around it. What all these stars share is a common condition. They are all nearing the ends of their lives. They have burned through most of their nuclear fuel. Their cores are contracting, heating, cycling through progressively heavier elements in fusion reactions that last shorter and shorter periods. Meanwhile, their outer envelopes have ballooned to extreme proportions, driven outward by the energy roaring up from below. They are shedding mass into space at rates that would strip away entire planets in a matter of years. They are pulsating, their radii fluctuating by 10 or 20 or even 30% over months and years. They are structurally unstable, maintained not by any robust equilibrium, but by a delicate and temporary balance that will inevitably fail. Every single one of these stars will die within the next few 100,000 years. Cosmically, that's the blink of an eye. Betelgeuse, VY Canis Majoris, UY Scuti, WO G64, NML Cygni, all of them are doomed. They will explode as supernovae, their cores collapsing into neutron stars or black holes, their outer layers blown outward in expanding shells of gas traveling at thousands of kilometers per second. For a few weeks, each of these explosions will outshine entire galaxies, billions of stars worth of light emanating from a single point in space, and then the light will fade, and all that will remain is an expanding cloud of enriched gas and a tiny, ultra-dense remnant at the center. It is worth pausing here to appreciate what we've encountered so far. We began with the Sun, a star 1.4 million kilometers across, a star that could hold over 1 million Earths, a star so large that light needs 4.5 seconds to cross it. And now we've reached stars with radii 1400, 1500, 1700 times larger. Stars that could hold trillions of Earths. Stars so vast that light needs hours to cross them. Stars whose surfaces, if placed at the center of our solar system, would extend past Jupiter, past Saturn, into the cold outer darkness where the giant planets roam. And yet, as extraordinary as these stars are, as vast and extreme and almost incomprehensible as their dimensions have become, there is something larger still. Because UY Scuti's claim to the title of largest known star did not go unchallenged. As measurements improved and new techniques were applied, a different star began to emerge as the leading candidate. A star buried deep in a cluster of red supergiants near the heart of the Milky Way. A star so remote and so heavily obscured by intervening dust that it was overlooked for decades. A star whose estimated size, if confirmed, surpasses everything we've discussed tonight. That star has a name, and the numbers attached to it are gonna push us past every boundary of scale we've encountered so far. Deep in the Milky Way, roughly 20,000 light-years from Earth, in the direction of the constellation Scutum, there exists a cluster of stars that most people have never heard of. It sits in one of the richest and most congested regions of the galactic plane, buried behind layer upon layer of interstellar dust that blocks visible light so thoroughly that you could point the most powerful optical telescope on Earth directly at this cluster and see almost nothing. The dust absorbs and scatters the shorter wavelengths of light, the blues and greens and even the reds, swallowing them before they can travel the vast distance between the cluster and our telescopes. For most of human history, this region of space was completely invisible to us. We had no idea it was there. We had no idea what it contained. The cluster was first identified in the late 1990s by an American astronomer named Charles Bruce Stephenson. Stephenson was conducting a survey of the sky in infrared light, wavelengths longer than visible red that can pass through the interstellar dust that blocks ordinary light. His survey revealed a grouping of massive, luminous red stars clustered tightly together in space. This grouping was designated Stephenson 2, the second such cluster identified in his survey. It was not, at first, considered particularly remarkable. Many star clusters exist throughout the galaxy, but as observations improved, as better infrared telescopes and more sophisticated analysis techniques became available, the true nature of Stephenson 2 began to emerge. This was not an ordinary cluster. It was one of the most massive concentrations of red supergiants ever found in the Milky Way. The cluster contains at least 26 red supergiants, an extraordinary number. Most star clusters contain only a handful of these rare, short-lived objects. Finding over 24 of them packed together in a single cluster suggested that this group of stars was both very massive and very young by astronomical standards, probably only around 15 to 20 million years old. The stars in Stephenson 2 were born together from the same giant molecular cloud, and the most massive among them had already evolved off the main sequence, swelling into red supergiants as their cores burned through their nuclear fuel at a ferocious pace. Try to imagine what this cluster would look like if you could see it up close. Picture a hypothetical planet orbiting a modest star within or near Stephenson 2. From the surface of that world, you would look up and see a night sky unlike anything visible from Earth. Instead of scattered pinpricks of white light, you would see over 24 bloated red supergiants hanging in the darkness. Each one would be enormous. Many of them would be individually larger than the orbit of Mars. Some would be large enough to stretch past the orbit of Jupiter. They would glow a deep, sullen red, each one visibly wider than any star visible from Earth's surface, each one a vast sphere of dying light. They would not twinkle the way stars do in our sky. They would sit there, heavy and ominous, enormous disks of dull crimson scattered across the firmament. Some would appear relatively close together, their reddish halos almost overlapping, creating the impression of a sky stained with smouldering embers. Others would be more isolated, lone giants burning slowly in the dark. The cumulative effect would be staggering. Not one dying giant, but dozens of them, all within the same small volume of space, all in the same terminal phase of their existence, all destined to explode within the astronomically near future. You would be living inside a graveyard of giants, a place where the largest and most violent objects the universe can produce are gathered together in extraordinary concentration, and among all of them, one would dominate. One would be visibly, unmistakably larger than all the rest. A star that, even in this company of colossal objects, stood apart. Among these red supergiants, one stood out. One was larger than all the others. One was larger, in fact, than any other star that had been reliably measured anywhere in the observable universe. That star is Stephenson 2-18, sometimes also catalogued as Stephenson 2DFK1. Stephenson 2-18 is a red supergiant, possibly a red hypergiant, with an estimated radius of approximately 2,150 times the radius of the Sun. Let that number land. 2,150 solar radii. Not 700 like Betelgeuse, not 1,400 like VY Canis Majoris, not 1,700 like UY Scuti. 2,150. This single measurement, if it is accurate, makes Stephenson 2-18 the largest known star by a significant margin. But what does 2,150 solar radii actually mean? What does it look like when translated from an abstract number into something you can attempt to visualize? Let's try. The Sun has a radius of approximately 696,000 kilometers. Multiply that by 2,150 and you get a radius of approximately 1.5 billion kilometers. The diameter from one edge of the star to the other is roughly 3 billion kilometers. 3 billion kilometers across. That is a single object stretching 3 billion kilometers. To ground this in our solar system, consider the following. If you place Stephenson 2-18 at the exact center of our solar system, replacing the Sun, its surface would extend outward past the orbit of Mercury, past the orbit of Venus, past the orbit of Earth, past the orbit of Mars, past the asteroid belt, past the orbit of Jupiter, and past the orbit of Saturn. Saturn orbits the Sun at an average distance of roughly 1.4 billion kilometers. The estimated radius of Stephenson 2-18 is approximately 1.5 billion kilometers. That means Saturn's orbit would be inside this star. Not just near the edge, inside. Everything within Saturn's orbit would be consumed. Mercury, Venus, Earth, Mars, Jupiter, Saturn, all of them would exist within the atmosphere of this single star. They wouldn't orbit it. They would be dissolved in it, their solid matter vaporized, their atmospheres stripped away, their entire existence reduced to trace elements dispersed in an ocean of stellar gas billions of kilometers wide. The asteroid belt, which sits between Mars and Jupiter and contains millions of rocky objects, would be deep within the star's interior. Even Jupiter, the largest planet in our solar system, a world so massive it contains more matter than all the other planets combined, would be little more than a droplet of material evaporating inside this star's impossibly vast envelope. Only Uranus, Neptune, and the distant objects of the Kuiper belt would remain safely outside, orbiting in the cold darkness beyond the star's swollen edge. Consider the volume. If Stephenson 2-18 has a radius 2,150 times the Sun's, then its volume is approximately 10 billion times the volume of the Sun. 10 billion suns could fit inside this object. And since the Sun itself can contain roughly 1.3 million Earths, the number of Earths that could fit inside Stephenson 2-18 is staggering. Roughly 13 trillion. 13 trillion Earths. Every human being on the planet could be given their own personal copy of the Earth. A full-size duplicate of our entire world with all its oceans and continents and mountains. And you could do this 13 trillion times over and still have room left inside a single star. Light needs roughly 4.5 seconds to cross the diameter of the Sun. To cross the diameter of Stephenson 2-18, light would need approximately 2 hours and 45 minutes. A beam of photons, traveling at the universal speed limit, 300,000 kilometers every single second, requires nearly 3 hours to get from one side of this star to the other. If you could somehow stand at one edge of Stephenson 2-18 and shine a flashlight toward the other side, your beam of light wouldn't arrive for almost 3 hours. And this is light. The fastest thing that can exist. Nothing in the universe travels faster, and even it needs hours to cross this object. The circumference of Stephenson 2-18, the distance you would travel if you flew around its equator, is approximately 9.4 billion kilometers. A commercial jet flying at 900 kilometers per hour would need roughly 1,200,000 years to complete one lap. You could have started your flight during the age when early human ancestors first began using crude stone tools, flown continuously for over 1,000,000 years through the entire evolution of the human species, and you would only now be completing a single circuit around one star. The luminosity of Stephenson 2-18 is estimated at approximately 440,000 times the luminosity of the Sun. It is one of the most luminous, cool stars ever observed. Despite this extraordinary output, you cannot see it with the naked eye. It is too far away, and the intervening dust between us and the star absorbs so much of its light that it is completely invisible without a telescope capable of seeing in infrared wavelengths. This colossal object, perhaps the largest single thing in the known universe, is hidden from direct human vision behind a curtain of cosmic dust. The surface temperature of Stephenson 2-18 is estimated at roughly 2,900 degrees Celsius. By stellar standards, this is cool. The Sun's surface is about 5,500 degrees Celsius. Hotter stars like Rigel can reach 12,000 degrees or more. But Stephenson 2-18's relatively low surface temperature is directly connected to its enormous size. The star's interior is generating a tremendous amount of energy, but that energy is being radiated from a surface area so inconceivably vast that the energy per unit area is relatively modest. The same total luminosity spread across a much larger surface means a cooler temperature at any given point on that surface. This is why Stephenson 2-18 glows a deep, dull red rather than the brilliant white or blue of hotter stars. If you could see it up close, it would appear as an immense, dimly glowing orb, its light a deep crimson that would cast everything in a blood-red hue. Like all the extreme stars we've discussed, Stephenson 2-18 is unstable. It pulsates, its radius swelling and contracting over irregular timescales. The exact amplitude of these pulsations is difficult to determine at its great distance, but they are likely significant, perhaps 10 to 20% of its total radius. That means the star's edge might fluctuate by hundreds of millions of kilometers over the course of months or years. An oscillation of hundreds of millions of kilometers. The entire distance from Earth to the Sun is about 150 million kilometers. Stephenson 2-18's breathing, its slow rhythmic heaving, covers a distance comparable to the gulf between Earth and the Sun with every pulse. The star is also shedding mass at an extreme rate. Material streams away from its surface, driven by radiation pressure and convective instability, forming an expanding shell of gas and dust around the star. Over its remaining lifetime, Stephenson 2-18 will lose a significant fraction of its current mass to space, contributing heavy elements and processed material to the interstellar medium. This material will eventually be incorporated into new molecular clouds, new collapsing cores, new stars, and new planetary systems. The atoms that make up Stephenson 2-18 today may one day form part of a rocky planet orbiting a young star that hasn't been born yet. Let's compare Stephenson 2-18 directly to the other contenders, because these comparisons sharpen the picture and help you appreciate just how far above the rest this star sits. Betelgeuse, the famous red supergiant in Orion, has an estimated radius between 700 and about 1,000 solar radii, depending on the study. Stephenson 2-18 at 2,150 solar radii, is roughly 2 to 3 times larger. If you placed both stars side by side, Betelgeuse, already enormous enough to engulf Mars, would look noticeably smaller. Stephenson 2-18 would dwarf it the way Jupiter dwarfs Earth. VY Canis Majoris, one of the most celebrated extreme stars in astronomy, has an estimated radius of roughly 1,400 to 1,500 solar radii. Stephenson 2-18 is approximately 40 to 50% larger again. VY Canis Majoris would reach toward the orbit of Saturn. Stephenson 2-18 would enclose it. UY Scuti, which held the popular title of largest known star for nearly a decade in public consciousness, has an estimated radius of roughly 1,700 solar radii. Stephenson 2-18 exceeds this by approximately 450 solar radii. That difference alone, that gap between UY Scuti and Stephenson 2-18, represents a span of more than 300 million kilometers. The gap between the second largest and the largest known star is itself larger than the distance from the Sun to Mars and back. WO G64, the red supergiant in the Large Magellanic Cloud, has an estimated radius of roughly 1,400 to 1,600 solar radii. NML Cygni in the constellation Cygnus has an estimated radius of roughly 1,300 to 1,700 solar radii. Both are extraordinary objects, easily in the top tier of stellar sizes, but both fall short of Stephenson 2-18 by a considerable margin. In every comparison, Stephenson 2-18 stands at the top. Not by a tiny margin that might be erased by a revised measurement, but by a substantial gap that places it in a category of its own among known stars. It is worth reflecting on what it would mean to exist near this object. Imagine a hypothetical planet orbiting at a safe distance beyond the star's bloated edge, far enough to receive only modest amounts of energy, perhaps orbiting at the distance where Uranus orbits our Sun. From the surface of that planet, looking inward, Stephenson 2-18 would fill the sky. You would not see a disk or a sphere. You would see a wall. A vast curved glowing wall of deep red light stretching from horizon to horizon in every direction you looked inward. The star would fill so much of the sky that you would have difficulty perceiving its curvature. It would simply be there, an immense, ever-present backdrop of dull crimson luminescence, covering a significant fraction of the visible sky. The light would be dim compared to what we experience on Earth, because the surface temperature is relatively cool, but the sheer extent of it, the overwhelming enormousness of the source, would make the experience unlike anything in human existence. You would feel small in a way that no experience on Earth could replicate. Not small the way you feel standing at the base of a mountain or looking out across an ocean. Small the way you might feel if you suddenly understood, viscerally and completely, that you are a mote of conscious matter drifting beside an object so large it could contain 13 trillion copies of your world. And even from that distance, you would be able to see the star's surface changing. The enormous convection cells, each one potentially as wide as the orbit of Mars, would slowly churn and shift over days and weeks. Darker regions would appear where cooler gas is sinking back into the interior. Brighter regions would form where hotter material rises to the surface. Occasionally you might see enormous ejections of material. Plumes of gas launched outward from the surface by internal instabilities, streaming into space and catching the faint red light as they expand. The star would not look static or serene. It would look restless, turbulent, alive in the way that only something on the verge of cataclysmic death can look alive. Because Stephenson 2-18 is dying. Like all the extreme stars we've discussed, it is nearing the end of its nuclear fuel supply. Its core is cycling through progressively heavier elements, each fusion stage shorter than the last. Within the next few 100,000 years, possibly far sooner, the core will reach the point where it can no longer sustain fusion. It will collapse under its own gravity in a fraction of a second. The outer layers, suddenly deprived of the outward pressure that supported them, will come crashing down onto the collapsing core and then rebound outward in a supernova explosion of unimaginable violence. For a few weeks, the explosion will outshine billions of ordinary stars. The shockwave will propagate outward through the surrounding star cluster, potentially disrupting gas clouds and triggering new rounds of star formation. After the explosion fades, all that will remain of Stephenson 2-18 is an expanding nebula of enriched gas and, at its center, a compact remnant. Depending on the mass of the remaining core, that remnant will be either a neutron star, a ball of matter roughly 20 kilometers across but containing more mass than the Sun, or a black hole, a region of space where gravity is so extreme that not even light can escape. Either way, the vast envelope of gas that once stretched past Saturn's orbit will be gone, scattered, returned to the interstellar medium from which it came. The cluster that Stephenson 2-18 belongs to is itself remarkable. Stephenson 2, also sometimes designated RSGC2, is one of the most massive young star clusters known in the Milky Way. It contains an estimated total mass of roughly 40,000 solar masses, spread across hundreds of stars. The cluster formed from a single giant molecular cloud, a vast reservoir of hydrogen gas and dust that collapsed under its own gravity and fragmented into hundreds of individual stars. The most massive of these stars, the ones born with 20 or 30 or 40 times the mass of the Sun, evolved the fastest. They burned through their hydrogen in only a few million years and are now in the red supergiant phase. Stephenson 2-18 is the most extreme among them, the star that swelled the farthest, the one that pushed closest to the upper limits of what stellar physics allows. The cluster's location is important. It sits near the base of the Scutum Centaurus arm of the Milky Way, one of the galaxy's major spiral arms. This region is rich in star-forming gas and dust, which explains why such a massive cluster could form here. But that same dust is what makes the cluster so difficult to observe. In visible light, the cluster is essentially invisible. Only by observing in infrared wavelengths, which can penetrate the dust, can astronomers study the individual stars. This is why Stephenson 2-18 was not discovered sooner. The technology to see it simply didn't exist until relatively recently. For most of the history of astronomy, from the ancient Greeks through the invention of the telescope, through centuries of painstaking observation, this star, quite possibly the largest discrete object in the known universe, was completely hidden from view. Think about what that means for a moment. For thousands of years, humans looked up at the night sky and catalogued the stars they could see. They named them. They mapped constellations. They built increasingly powerful telescopes to see fainter and more distant objects. And through all of that effort, the largest star we know of was invisible. It was sitting there, 20,000 light years away, enormous beyond comprehension, pouring 440,000 times the sun's energy into space, and we couldn't see it. The universe was keeping its biggest secret behind a curtain of dust. It wasn't until infrared astronomy matured in the latter decades of the 20th century that objects like Stephenson 2-18 became accessible. The 2-micron all-sky survey, a comprehensive mapping of the sky in near-infrared light completed in the early 2000s, was instrumental in identifying and cataloguing stars in heavily obscured regions like the one containing Stephenson 2. Follow-up observations with more powerful infrared instruments allowed astronomers to measure the temperatures and luminosities of individual stars in the cluster, and from those measurements, to estimate their radii. The figure of 2,150 solar radii for Stephenson 2-18 comes from this kind of analysis. Astronomers measured the star's apparent brightness in infrared, estimated its distance based on the cluster's known location in the galaxy, corrected for the dust between us and the star, and used the relationship between luminosity, temperature, and surface area to calculate the radius. And that radius, 2,150 times the sun's, is what places Stephenson 2-18 at the top of every list of the largest known stars. It is the current best answer to the question, what is the biggest star we've ever found? But as we're about to discover, that answer comes with enormous caveats. The measurements that produce this number are based on a chain of assumptions and estimations, each one introducing uncertainty. The true size of Stephenson 2-18 might be somewhat larger or somewhat smaller than 2,150 solar radii. The ranking of the largest known stars is not settled science written in stone. It is a snapshot of our best current understanding, subject to revision as new data arrives and old measurements are refined. And the reasons for that uncertainty, the reasons why pinning down the size of these extreme stars is so fiendishly difficult, are themselves a fascinating story. One that reveals as much about the limits of human knowledge as it does about the stars themselves. So we've arrived at Stephenson 2-18, a star with an estimated radius of 2,150 times the sun's, an object so enormous that it could swallow everything in our solar system out past the orbit of Saturn. We've climbed the ladder of stellar size from ordinary red giants to supergiants to hypergiants, each step revealing something more extreme than the last. And now, standing at the top of that ladder, looking at the current leading candidate for the largest known star in the universe, we need to confront an uncomfortable truth. We're not entirely sure this answer is correct. Not because anyone is lying or because the science is bad, but because measuring the true size of the most extreme stars is one of the hardest problems in all of observational astronomy. The numbers we've been discussing, all those radii expressed in confident multiples of the sun's size, are not measured the way you might measure the width of a table with a ruler. They are estimated. They are inferred through chains of reasoning that stretch across multiple techniques, each one introducing its own uncertainties. And when you stack those uncertainties on top of one another, the final number can shift by a surprising amount. Let's walk through how astronomers actually determine the size of a distant star, because understanding the method is the only way to understand why the answer keeps changing. The most fundamental approach relies on a simple relationship that connects three properties of any star: luminosity, temperature, and radius. If you know how much total energy a star is radiating, its luminosity, and you know the temperature of its surface, then you can calculate its radius. This works because a star's luminosity depends on both how hot its surface is and how large that surface is. A hotter surface radiates more energy per square meter. A larger surface has more square meters to radiate from. The mathematical relationship, known as the Stefan-Boltzmann law, says that luminosity equals 4 times pi, times the radius squared, times the Stefan-Boltzmann, constant times the temperature to the 4th power. If you measure luminosity and temperature, you can solve for radius. Simple in principle, extraordinarily difficult in practice. The first challenge is measuring the star's luminosity. You can't directly measure how much total energy a star is putting out. What you measure is how bright the star appears from Earth, its apparent brightness. To convert apparent brightness into true luminosity, you need to know the distance to the star. A star that appears dim might be intrinsically faint and nearby, or it might be incredibly luminous and very far away. You cannot tell the difference without knowing the distance. And here is where the problems begin. Distance is one of the hardest things to measure in astronomy. For relatively nearby stars, within a few thousand light years, astronomers can use a technique called parallax. As Earth orbits the Sun, our perspective shifts slightly, and nearby stars appear to wobble back and forth against the background of more distant stars. By measuring this wobble, you can calculate the distance using basic trigonometry. Think of it like holding your thumb at arm's length and closing one eye, then the other. Your thumb appears to shift against the background. The amount it shifts tells you how far away it is. Parallax works the same way, except instead of switching eyes, astronomers use the 2 positions Earth occupies 6 months apart on opposite sides of its orbit around the Sun, separated by about 300 million kilometers. Even across that enormous baseline, the wobble of distant stars is incredibly tiny. The farther away a star is, the smaller its apparent wobble, and the harder it is to measure. The European Space Agency's Hipparcos satellite, launched in 1989, measured parallaxes for over 100,000 stars and revolutionized our understanding of stellar distances. Its successor, the Gaia spacecraft, launched in 2013, is measuring parallaxes for nearly 2 billion stars with unprecedented precision. Gaia can detect wobbles so small that they correspond to the apparent width of a human hair seen from 1,000 kilometers away. That level of precision is almost unimaginable. But even Gaia has limits. The farther away a star is, the smaller its parallax wobble becomes, and the harder it is to measure accurately. For a star like Stephenson 2-18, located roughly 20,000 light-years from Earth, the parallax is so tiny that even Gaia's extraordinary precision produces measurements with significant uncertainty. And that distance uncertainty feeds directly into the luminosity calculation. If Stephenson 2-18 is actually 22,000 light-years away instead of 20,000, it's inherently more luminous than we thought, because the same apparent brightness at a greater distance means the star must be putting out more light. And if it's more luminous, the radius calculation gives a larger answer. Conversely, if the star is closer than we think, say 18,000 light-years, then it's less luminous, and the calculated radius shrinks. A 10 to 15% uncertainty in distance can produce a 20 to 30% uncertainty in the estimated radius. For Stephenson 2-18, that could mean the difference between a radius of 1,800 solar radii and 2,400 solar radii. The star could be somewhat smaller than the current estimate or substantially larger, and we cannot pin it down more precisely without better distance measurements. This is not a theoretical problem. It has already changed the rankings in real time. VY Canis Majoris offers the most dramatic example. In the early 2000s, several studies estimated VY Canis Majoris' radius at over 2,000 solar radii. At the time, it was widely cited as the largest known star. Then, in 2012, a team of astronomers using improved distance measurements from radio observations of the massive emissions surrounding the star determined that VY Canis Majoris was somewhat closer than previously thought. It was not 1,500 parsecs away, as some earlier estimates had suggested, but closer to 1,170 parsecs. This seemingly modest revision in distance had a dramatic effect. Because the star was closer than assumed, it was less luminous than assumed, which meant its calculated radius dropped significantly, from over 2,000 solar radii down to roughly 1,400 to 1,500. The star didn't physically shrink. It didn't change at all. Our understanding of it changed. A better distance measurement erased nearly a third of its estimated size overnight. VY Canis Majoris went from the undisputed largest known star to merely one of several contenders, all because of a distance correction. This is the fragility of stellar size measurements. They are only as good as the data they rest on, and the data can change. The problem is compounded by interstellar dust. Stephenson 2-18 sits behind an enormous quantity of dust between us and it. This dust doesn't just hide the star from visible light. Even in infrared wavelengths, where the dust is more transparent, it still absorbs and scatters some of the light. Astronomers must estimate how much light the dust has removed and correct for it. This correction, called extinction, is itself uncertain. Different studies using different extinction models can arrive at different corrected luminosities for the same star, which leads to different radius estimates. The dust acts like a dirty window between us and the star. We can see through it, but we're never quite sure how much the window has dimmed or reddened the view. For stars embedded deep in the galactic plane, like Stephenson 2-18, the extinction can be substantial, several magnitudes of dimming, meaning the correction is large and any error in that correction is amplified in the final radius estimate. The second major challenge is measuring the star's surface temperature. For most stars, you determine the surface temperature by analyzing the star's spectrum, the pattern of light it emits at different wavelengths. Hotter stars emit more blue light. Cooler stars emit more red light. By fitting the observed spectrum to theoretical models, astronomers can estimate the temperature. But for the most extreme red supergiants, this analysis is complicated by the star's own atmosphere. These stars are surrounded by thick envelopes of gas and dust, much of which they've ejected themselves. The material surrounding the star absorbs and re-emits light, altering the spectrum in ways that can be difficult to disentangle from the light of the star's actual surface. Molecules form in the cooler outer layers of these stars, particularly titanium oxide and water vapor, and these molecules create complex absorption patterns in the spectrum that make it harder to determine the true underlying temperature. A temperature estimate that is off by just a few hundred degrees Celsius can shift the calculated radius by hundreds of solar radii. And because temperature enters the Stefan-Boltzmann equation raised to the fourth power, even a small fractional error in temperature produces a much larger fractional error in the derived radius. Getting the temperature wrong by 10% could shift the radius by nearly 50%. These are not forgiving calculations. There is another technique astronomers sometimes use called angular diameter measurement. If you can directly measure how wide a star appears on the sky, its angular diameter, and you know its distance, you can calculate its physical diameter for very large, relatively nearby stars like Betelgeuse. This is possible using a technique called interferometry, where the light from multiple telescopes is combined to achieve the resolution needed to see the tiny angular size of the star. Betelgeuse is close enough and large enough that its disk can actually be resolved. We can see it as a tiny circle rather than a point of light. Interferometric observations of Betelgeuse have revealed details on its surface, including bright spots and dark patches produced by those enormous convection cells we discussed earlier. These direct images have given us some of the most reliable radius measurements for any supergiant star. But for more distant stars like Stephenson 2-18, which is roughly 20,000 light-years away, the angular diameter is so small that no current instrument can resolve it directly. The star appears as a point of light even in our most powerful telescopes. We cannot see its disk. We cannot directly measure how wide it is. We must rely entirely on the indirect method of combining luminosity and temperature to calculate the radius. And here is where a subtler and perhaps more profound problem enters the picture. Even if we could measure everything perfectly, even if we knew the distance to the last light year, the extinction to the last fraction of a magnitude, the temperature to the last degree, there is a fundamental ambiguity in what the size of these stars even means. Because the largest stars don't have surfaces. Not in any normal sense of the word. When you think of a surface, you think of a boundary. A clear edge where the object ends and empty space begins. Earth has a surface. You're standing on it. The boundary between the ground and the air is sharp and obvious. Even gas giants like Jupiter have a definable layer where the atmosphere becomes opaque enough that we can't see deeper. We call that the cloud top layer, and it serves as a useful boundary. But the most extreme red supergiants and hypergiants don't have anything like this. Their outer layers fade gradually into space. There is no crisp edge. Instead, there is a slow, continuous transition from regions that are clearly part of the star, dense enough to be opaque, to regions that are clearly interstellar space, with essentially nothing in them. Between those two extremes is a vast zone of ambiguity where the gas gets progressively thinner and thinner, fading from something you might call stellar atmosphere into something you might call circumstellar envelope, into something you might call empty space. Where exactly do you draw the line? To understand why this matters, think about our own planet. Earth's atmosphere doesn't have a sharp boundary either. At sea level, the air is dense. You breathe it. You feel the wind. But as you climb higher, the atmosphere thins. At the summit of Mount Everest, roughly 9 kilometers up, the air is already so thin that most humans cannot survive without supplemental oxygen. At 40 kilometers, you're above 99% of the atmosphere's mass. At 100 kilometers, the internationally recognized Kármán line, the air is so sparse that an aircraft could not generate lift, and we conventionally say you've reached space. But there is no wall at 100 kilometers. There is no sharp boundary where air ends and vacuum begins. Gas molecules are still present at 200 kilometers, at 400, even at 1,000. They just get rarer and rarer. The International Space Station orbits at about 400 kilometers and still experiences faint atmospheric drag. Satellites at 800 kilometers occasionally need to boost their orbits because trace atmosphere slows them down. The number 100 kilometers is a human convention, a useful line drawn in a gradient for practical purposes. It doesn't correspond to a physical boundary. Now imagine this same problem, but instead of a gradient zone 100 or 1000 kilometers thick, the gradient zone is tens of millions or even hundreds of millions of kilometers thick. That is the situation with the most extreme red supergiants. The gas thins so gradually across such a vast radial distance that deciding where the star ends is genuinely ambiguous. A reasonable person could draw the line at one radial distance and get a radius of 1800 solar radii. Another equally reasonable person, using a slightly different definition of where the photosphere sits, could draw the line further out and get 2200. Neither is wrong. They're applying different but legitimate criteria to a physical situation that doesn't have a clean answer. The star doesn't know where its surface is. It just gradually dissolves into the vacuum of space over a distance wider than Earth's entire orbit around the Sun. Astronomers typically define the surface of a star as its photosphere, the layer from which most of the star's light escapes directly into space. Below the photosphere, the gas is dense enough that photons are absorbed and re-emitted many times before escaping. Above the photosphere, the gas is thin enough that photons can travel freely outward. This is a useful definition, and it works well for stars like the Sun, where the photosphere is a relatively thin, well-defined layer. The Sun's photosphere is only about 500 kilometers thick. Compared to the Sun's total radius of roughly 696,000 kilometers, the photosphere is a razor-thin shell. The transition from opaque to transparent happens over a very short distance. There is a clear, well-defined surface, but for the most extreme supergiants, the photosphere itself can be diffuse and ill-defined. The transition from opaque to transparent happens gradually over an enormous distance, not in a thin, crisp shell. The photosphere might extend across tens of millions of kilometers of radial distance, making the concept of a single sharp radius somewhat artificial. Furthermore, these stars are surrounded by extended atmospheres and circumstellar envelopes that blur the boundary even further. VY Canis Majoris, for example, is surrounded by a vast complex nebula of expelled material that extends far beyond the photosphere. Is that nebula part of the star? Most astronomers would say no, it's ejected material. But where does the star's atmosphere end and the ejected material begin? The boundary is fuzzy. Different measurement techniques can probe different layers of the star's extended atmosphere. And depending on which technique you use, you might get a different answer for the radius. This is why different studies often produce different sizes for the same star. A study using one infrared wavelength might probe a different atmospheric layer than a study using a different wavelength. One team might use one set of theoretical models to interpret the data, while another team uses a different set. Neither is necessarily wrong. They're measuring slightly different things, or interpreting the same data through different but equally valid frameworks. The result is a range of estimates rather than a single definitive number. This uncertainty is why the title of largest known star has changed hands multiple times over the past 2 decades. In the early 2000s, VY Canis Majoris was widely cited as the largest, with some estimates placing its radius above 2,000 solar radii. As measurements were refined and new techniques were applied, those estimates came down to roughly 1400 to 1500 solar radii. Meanwhile, UY Scuti emerged in 2012 with an estimated radius of 1700 solar radii, taking the crown. Then, Stephenson 2-18 emerged as the leading candidate with its estimate of 2,150 solar radii. Each time the ranking shifted, it wasn't because a new star was discovered that was obviously and indisputably bigger. It was because the estimates for existing stars were revised, sometimes upward, sometimes downward, as better data became available, and the revisions will continue. Future observations, particularly those from the Guiu spacecraft, as it refines its distance measurements, and from next-generation infrared telescopes that can probe the atmospheres of distant supergiants in greater detail, will almost certainly produce revised size estimates for many of these stars. Stephenson 2-18 might get larger, it might get smaller. UY Scuti might turn out to be closer to 2,000 solar radii than 1,700, leapfrogging back into contention. A completely different star, one that hasn't even been properly measured yet, might emerge as the new record holder. The list of the largest known stars is a living document, constantly being updated as our instruments improve and our understanding deepens. There may even be larger stars out there that we simply haven't found yet. The Milky Way contains hundreds of billions of stars. We've only measured the sizes of a tiny fraction of them. Heavily obscured regions of the galaxy, particularly near the galactic center and along the spiral arms where dust is thickest, could harbor undiscovered red hypergiants, even larger than Stephenson 2-18. We would have no way of knowing until someone points an infrared telescope in the right direction and takes the right measurements. The universe is under no obligation to have shown us its largest star yet. But here is what I think matters most about all of this. The exact ranking, whether Stephenson 2-18 is truly number one, or whether some other star eventually claims the title, is in a sense less important than the broader reality these stars reveal. Because regardless of which specific star holds the record at any given moment, the fundamental fact remains the same. Stars exist that are so large they could contain most of our solar system. Objects exist in this universe that stretch billions of kilometers across, that light needs hours to traverse, that could hold trillions of copies of our world within their volumes. Whether the largest one has a radius of 2,150 solar radii, or 1,900 or 2,300, doesn't change the essential truth of what these objects represent. They represent the upper boundary of what matter can do under the laws of physics. They are the largest single coherent structures that gravity and nuclear physics can produce. Galaxies are larger, but galaxies are collections of separate stars. Nebulae are larger, but nebulae are diffuse clouds without a central binding structure. These extreme stars are individual objects, single entities held together, however loosely, by their own gravity, radiating energy from their own internal nuclear furnaces. And they are enormous, not just larger than Earth, not just larger than our solar system's planets, but larger than most of the space we consider our solar system. This should change how you think about the night sky. When you look up and see the stars as tiny points of light, your brain interprets them as small things far away. But some of those points of light are not small. Some of them are objects so vast that the human mind cannot truly grasp their extent. Betelgeuse, the reddish dot on the shoulder of Orion, is an object that could swallow the orbit of Mars. Antares, the red heart of Scorpius, could do the same. And Stephenson 2-18, invisible to the naked eye, hidden behind 20,000 light years of dust, could engulf everything from Mercury to Saturn. These stars also tell us something profound about time. Every one of these extreme stars is dying. Their enormous sizes are not signs of vitality. They are signs of approaching death. A star swells to these dimensions because its core is running out of fuel, because the internal balance that sustained it for millions of years is failing. The very thing that makes these stars so spectacular, their bloated immensity, is the symptom of a terminal condition. Within the next few 100,000 years, every star we've discussed in this category will be gone. Betelgeuse will explode, VY Canis Majoris will explode, UY Scuti will explode, Stephenson 2-18 will explode. Their outer layers will be scattered across space. Their cores will collapse into neutron stars or black holes. The largest objects in the stellar zoo will be replaced by some of the smallest and densest objects in the universe. But from those explosions, new things will emerge. The material scattered by these supernovae will enrich the surrounding interstellar medium with heavy elements, carbon, oxygen, silicon, iron, the building blocks of rocky planets and living organisms. Future generations of stars will form from gas clouds seeded with these elements. Future planets will coalesce from the debris. Future worlds might develop conditions suitable for life. The atoms that are currently part of Stephenson 2-18 may, billions of years from now, be part of a mountain on a distant world, or part of an ocean, or part of a living creature that looks up at its own night sky and wonders about the stars. This is the cycle of stellar evolution. Stars are born from clouds of gas. They burn for millions or billions of years. The most massive ones swell to extraordinary sizes near the end of their lives. They explode, seeding space with the elements they forged in their cores. Those elements become part of new stars and planets. It is a cycle that has been running for nearly 13.8 billion years, since the first stars formed in the young universe, and it will continue for trillions of years into the future, long after every star alive today has died. Our own sun will participate in a modest version of this cycle. In about 5 billion years, it will swell into a red giant, engulfing the inner planets. It won't become anything close to a star like Stephenson 2-18. It's far too small for that. It will reach perhaps 100 or 200 solar radii, a respectable size but nowhere near the extremes we've explored tonight. After shedding its outer layers, it will leave behind a white dwarf, a glowing ember roughly the size of Earth that will slowly cool over trillions of years. That will be our sun's legacy. A small, quiet remnant glowing faintly in the darkness. But the atoms that currently make up the sun, the hydrogen and helium that fuel its core, the trace amounts of heavier elements in its outer layers, these atoms have their own history. Many of them were forged inside a previous generation of stars. Stars that lived and died before the sun was born. Some of those ancient stars might have been red supergiants, possibly even objects approaching the scale of the monsters we've discussed tonight. We will never know for certain, because those stars exploded billions of years ago, and their individual identities have been lost to time. But their material lives on, recycled into new stars, new planets, and eventually into us. The iron in your blood was forged in the core of a massive star that lived and died before the sun existed. The calcium in your bones, the oxygen you breathe, the carbon that forms the basis of every molecule in your body, all of it was produced inside stars. You are quite literally made of stellar material, and some of that material may have once been part of a star as extreme and enormous as the ones we've explored tonight. So when we talk about the largest star in the universe, we're not just talking about a record in a catalogue. We're talking about the most extreme expression of a process that connects everything in the cosmos. The same physics that makes the sun shine, nuclear fusion converting light elements into heavier ones and releasing energy in the process, is the physics that drives a star like Stephenson 2-18 to swell past the orbit of Saturn. The same gravity that keeps your feet on the ground is the gravity that holds these bloated stellar atmospheres together, however tenuously. The same elements that make up your body were forged in the cores and scattered in the explosions of stars like these. And there is something about this knowledge that should stay with you long after tonight. Consider what we've accomplished as a species. We live on a small rocky planet orbiting an average star in one arm of an ordinary spiral galaxy. We've existed for roughly 300,000 years, a blink of an eye in cosmic terms. And yet, from this tiny perch, using nothing but our curiosity and our intelligence, we've managed to detect, measure, and understand objects so large that light needs hours to cross them. We've figured out why they exist, how they formed, why they pulsate, why they shed mass, and how they will die. We did this across distances of 20,000 light years, peering through curtains of interstellar dust that hid these objects from every generation of humans before our own. The first humans to look up at the night sky saw the same stars we see, but they could not know what those stars were. They could not know their sizes, their temperatures, their distances, or their fates. They saw lights in the darkness and wove stories to explain them. And now, after thousands of years of accumulated observation, experiment, and mathematical reasoning, we can say with reasonable confidence that somewhere in the direction of the constellation Scuti, buried deep in the galaxy, there is a single object roughly 3 billion kilometers across. We know this. We measured it. And the chain of reasoning that led us to this measurement, from parallax to photometry, to spectral analysis to theoretical stellar models, is one of the great intellectual achievements of our species. It is a monument to what persistent curiosity can accomplish. The universe doesn't owe us comprehensibility. There is no reason why the cosmos should be structured in a way that human minds can understand. And yet, to a remarkable degree, it is the same mathematics that describes the trajectory of a thrown ball, describes the orbit of a planet around a star. The same physics that explains a candle flame explains the nuclear furnace at the heart of the sun. The laws are consistent, and they are discoverable. We have discovered them. And through those laws, we've learned that the universe builds things of staggering scale, objects so large they humble every structure humans have ever built, every distance humans have ever traveled, every volume humans have ever contemplated. Let's take a moment to remember how far we've traveled tonight. We started with the sun, an object so large it could hold over 1 million Earths, an object so dominant that it contains 99.86% of all the mass in our solar system. We thought the sun was big. Then we met Arcturus, 25 times wider. Its surface would swallow Mercury without hesitation. We met Aldebaran, 44 times wider, reaching toward Venus. We met Rigel, 79 times the Sun, a blazing blue supergiant that would scorch the inner planets to glass. Each one seemed enormous, each one dwarfed the last, and then we crossed into the realm of the red supergiants, Antares, 680 times the sun's radius, a star that would consume Mercury, Venus, Earth, and Mars. An object so wide that a commercial jet would need over 100,000 years just to cross it. And Betelgeuse, possibly over 1,000 solar radii, pulsating and unstable, reaching toward the orbit of Jupiter. Stars so large that light itself needs hours to traverse them. Stars that made the sun look like a marble beside a house. And then we went further. VY Canis, Majoris, at 1400 to 1500 solar radii, approaching Saturn's orbit. UY Scuti at 1700, a star so enormous that 6.5 trillion Earths could fit inside it. And finally, Stephenson 2-18 at 2150 solar radii, a star whose diameter stretches 3 billion kilometers. A star that could swallow Mercury, Venus, Earth, Mars, Jupiter, and Saturn. A star so wide that light needs nearly 3 hours to cross it. A star that could contain 13 trillion copies of our world. From the Sun to Stephenson 2-18, we multiplied the radius by more than 2,000. We went from a star that seemed impossibly large to an object that makes that star look like a grain of sand beside a house. And at every step, the universe had more to show us. More scale, more extremity, more evidence that the cosmos operates on dimensions that human intuition was never designed to grasp. And yet we grasped them anyway. We measured them, we calculated them, we understood them. Not perfectly, not completely, but enough. Enough to know that these objects exist. Enough to know why they're so large. Enough to know that they're dying, and that from their deaths, new worlds and possibly new life will one day emerge. The largest star in the universe is bigger than you think. Not just because the numbers are large, not just because the comparisons are staggering, but because the story behind those numbers connects you to the entire history and future of the cosmos. These stars are the engines that built the periodic table. They are the furnaces that cook the raw material of the universe into the rich diversity of elements that make planets and life possible. They live briefly, burn furiously, swell to incomprehensible dimensions, and die violently, seeding the universe with the complexity it needs to produce worlds like ours. Whether Stephenson 2-18 holds the exact record today, whether it will hold it tomorrow, whether some undiscovered star buried deeper in the galactic dust is even larger, the essential truth doesn't change. The universe builds objects of staggering scale. Stars so large they could swallow the solar system. Stars so large that light needs hours to cross them. Stars so large that our planet, our home, our entire civilization would be less than a rounding error within their volumes. And you are here on a small rocky world orbiting a modest star, able to know this, able to measure it, to calculate it, to imagine it. You are a collection of atoms that were forged inside ancient stars, arranged into a pattern complex enough to look back at the universe and understand what it sees. You are a stardust that became conscious, matter that learned to ask questions about itself. And tonight, you use that consciousness to contemplate objects billions of kilometers wide, objects that dwarf everything in your daily experience by factors so large they cease to have intuitive meaning. You held those ideas in your mind. You followed the chain of reasoning from our modest sun to red giants, to supergiants, to hypergiants, to the very edge of what stellar physics permits. And now, you know something that most people will never know. Not just that big stars exist, but why they're big, how we know they're big, and why the answer is more uncertain and more fascinating than a simple number on a list. The next time you step outside on a clear night and look up, find Orion. Look for the reddish dot at the shoulder. That's Betelgeuse, a star so large it could engulf the inner solar system. And as you look at it, remember that somewhere far beyond it, invisible to your eyes, hidden behind 20,000 light years of dust and gas, there is something far larger. Something that could swallow nearly the entire solar system. Something that is slowly, magnificently, catastrophically dying. And when it finally explodes, its atoms will drift through space for millions of years, joining clouds of gas that will one day collapse to form new stars and new planets. And perhaps on one of those planets, something will look up at its own night sky and wonder about the stars. Just as you are doing right now, that connection across billions of kilometers and billions of years, from the largest stars that have ever existed to the small conscious beings who measure them, is what makes this story worth telling. The largest star in the universe is bigger than you think, but so is the fact that you can think about it at all. Thank you for joining me on this journey through the most extreme objects in the stellar universe. If you found this exploration valuable, a like or subscribe would mean a great deal. It helps this channel continue making these deep explorations of the cosmos. And remember, those points of light aren't all the same. Some of them are modest stars like our sun. Some of them are red giants a few dozen times wider. And somewhere out there, hidden behind curtains of interstellar dust, are stars so enormous that our entire solar system could fit inside them with room to spare. They are the largest things that have ever existed. They are dying, slowly, spectacularly, inevitably. And from their deaths, new worlds will be born. Good night. And may you never look at the stars the same way again.